Okay, cool. Okay. Yeah, we will start now with discussing Goodstein theorem, a new chapter. And so this covers finite trees. Now there are different definitions of finite trees. Therefore, we choose one. But the Goodstein theorem works for all sorts of trees. Okay, finite tree. Now make it this. I speak about non-finite trees. It's finite set consisting of a set of nodes in tree relation such that we have two properties. P has a minimal element. Minimum R and P. Such that for T and P, here R is called the root of T. Second, for all open T is the set of A and T, A before B, linearly ordered. Linear ordering. Actually, you have seen this definition before. So what is the shape of a tree? Something like this. Here's the root. And if you have some node, and we look downwards, these points stay on a line. So this is linear ordering. If you look downwards here, the linear ordering. Now we can consider this figure in space. And if we turn around, you see from the back, the tree looks like this. And this is the same tree as this one. That's a version of having non-planar trees. If you have planar trees, consider the concrete drawing, and then this is the right subtree, and the thing is now it's the left immediate subtree. So that is the explanation for non-planar. Now, if you have this definition, then you can define following notion for A and B and C. Exists even human of A and B. So what is this? Well, you have here A and B. And then there's a lower bound, namely the root. This is the greatest lower bound, and this is here the inferior A and B. How to find it? Well, you go from A down to the B down to the, there will be the first point where this path will meet, and that's inferior. Next definition of homomorphic embedding. I write just S and T for the tree structures, and E are finite tree. So I drop now the mentioning of the O-rings. Okay. We write that is homomorphically embeddable into T. Symbols as embeddable T. If, embedding could of course be a function. If there is function H from S into T, 1 to 1, such that for all A and B and firstly, if we have the infimum of A and B in S and map it as H, then it's the infimum in T of H of A and of B. So this has a property that the tree S somehow sits naturally in a tree T. Now you cannot see directly what the effect is, but if S embeds into T, the number of nodes is of course less than or equal to the number of nodes here, because H is injective, 1 to 1. But moreover, you can easily show that if you have such an embedding and you have a node in tree S, let's say this node match to this node, you see the number of direct successors is 2. In the image point, the number of direct successors of the image point has to be at least as big as the number of direct successors over E. So the branching is respected, the height is respected. Okay, that's definitions. Now out of the blue comes the theorem. Point 1, Goodstein. And it's easy to write. For all infinite sequences of finite trees, the excess number of I and J, I of this and J, and I is embedded in J. That's all. Now, it's normally not covered in discrete mathematics, but of course it belongs to the area of discrete mathematics. And now I will prove this. And the proof is mysterious in the sense, first of all, normal mathematicians will have no chance to prove this. Because you start with finite objects and then you play a bit around with notions. But this cannot be proved in strong systems of analysis. So you need to go to a very strong system. You will see in a minute what's going on. So this is the goal. And you can try for half an hour, and normally you will not succeed. You can try it for 1 week, you will normally not succeed. You can try it for half a year. And if you don't know the proof, you will not succeed. But now I will show the proof. And actually, there are people claiming that the proof coming now belongs to the most beautiful proofs which have ever been done in mathematics. So now I hope that you are curious. Now we start a bit more abstract. The quasi order is here. This O-ring such that this O-ring is reflexive and transitive. Okay, nothing special. and quasi order. It's called well quasi ordering. If for all infinite sequences of elements in Q, the exists I, S, and J. One is in J and QI is available in QJ. And the sequence, an infinite sequence QI, all that. If it does not satisfy this condition, if for all I and J, if I less than J, then QI is not available. So in other words, it's the quasi order if and only if there is no infinite bad equals. Okay. Now comes the first trick, namely we want to have closure properties. So if you start with the well quasi order, you can take disjoint unions and you can ask what's going to happen with that structure. It's somewhat easy to show that disjoint unions is natural ordering form of well quasi order. Then you do Cartesian products of well quasi orders with natural ordering. It is also well quasi order. Of course, you want to see an example where every well order is a well quasi order. It's easy to see, right? Because in a well order, there's no strictly decreasing sequence, and here's this immediately. So the natural numbers form a well quasi order. That's all this nice and easy structure theory. But we start already with a difficult example, namely, we go to finite sequences. Let's get Newton. Let be a quasi order. Okay. Q star is a set of finite sequences over Q. This is Q0, K minus 1. Q L is an element in Q. K is 0. K equal to 0 covers the empty sequence. Now, here we have the notion of homomorphic embedding. Let us consider something comparable to finite sequences. Now we define a notion. As follows, namely, we have here a sequence Q1, K minus 1. And this is embedded into sequence Q1, 1, Q, K prime minus 1 prime. This sequence somehow embeds into subsequence. So they exist in this case. It takes indices I0 up to I K minus 1, such that they are integrated. And for all L smaller than K, we have 2L embeds into Q prime I. So what does this mean? You take the sequence here and you take Q0, and then you look for the first point here where you can embed Q0. Then you take Q1, and then you look to the right of this point. Where's the next one where you can embed Q1, etc. And when this is going to terminate, then you have found those ones, and then you can embed the left hand side and the right hand side. It could be that it's not going to work when you don't find partners for the element on the left hand side. And then this only means that the sequence on the left hand side is not embeddable into the right hand side. Okay. And now it comes theorem. If you with then you start. It's here's okay. How to prove this? Actually, the proof of this one is already difficult. So when you want to try it, you can try hard and it will fail. That's already quite strong. And maybe you will succeed, but it will cost you some energy. Proof. How it comes. So okay, we want to prove that this one is a Bell quasi order. So assume that this is wrong. Assume that this is not a Bell quasi order. Then there is an infinite bad sequence. So not a Bell quasi order. Then there is an infinite bad sequence. Okay, now comes the trick, namely we form a special bad sequence. So let's E0 be first member of an infinite bad sequence such that the length of the sequence is minimal. So the length of this sequence is well, K, right? So we have the K main elements. So now we have the world of bad sequences, and now we zoom in into the first coordinates. And the first coordinates all have a finite length. So there will be a bad sequence where the length of the starting term is minimal. Just you have a set of natural numbers, namely the length of the first elements of bad sequences, and then you can just choose a minimal natural number. So let this T0 be such that exists a bad sequence this 0 and the length of T0 is minimal possible. Okay. Now we consider all bad sequences starting with T0. Among all bad sequences starting with T0, there will be one where the length of the second element is minimal. Let's see. P1, P1, such that there is infinite bad sequence starting with 0, P1 and such that the length of P1 is minimal. And then you continue. Find another sequence where the third element is minimal length, and then you iterate. Now, okay. What do we obtain? You obtain an infinite sequence. Yeah, I'm 0 to infinite. And this is bad sequence. This is a bad. Why is this a bad sequence? Well, assume I have this in J. I want to show that Ti is not embeddable in Tj. Then the construction. There is a bad sequence. Starting with T0, T1, Ti, Tj, etc. Now, since this sequence, but be careful, this sequence is not this sequence, right? But by construction of this sequence, we know at finite amount of time, every initial segment extends to bad sequence. But since this sequence is bad, I cannot be embeddable in Tj. And so I not embeddable in Tj. Okay. So that's the first trick in the proof. From a bad sequence, we go to the so-called minimal bad sequence. And that's a famous argument by Nash-Williams. So we have the minimal bad sequence. Okay. Now the question is, so what? There's no problem here. Just from one bound example, we found an bound example. It's of properties. Okay. Now you see that L is not the empty sequence for all L. But once it's the case, Well, we apply this for k equal to 0. Then the empty sequence is embeddable in any sequence because it's an empty quantifier. And you can imagine that the empty sequence is somewhat trivial, and the definition should be made up in a way that the empty sequence embeds into everything. Okay, so we can write this sequence element TL. Write TL as first element, the element in Q, extended by some rest. SL is a finite sequence of elements in Q, and QL is an element. Q is QL in Q, SL in Q star. Not much has happened yet. Now we make a claim. We claim that we have a new sequence SK from 0 to infinity. We claim that this sequence has no infinite bad subsequence. Now, why is this the case? Well, otherwise, there exists sequence AI of indices here, quickly including that's fine. And SKI is bad. Okay. So what? Now we make the new situation. Consider sequence 0 E k0 minus 1. Now comes sk0, sk1, etc. What can we say about the sequence? The sequence is bad. Why is this bad? Well, make up a case distinction to assume I live in here. Now the different options depending on where the indices are distributed. If I and j are in this interval, so if j is this in k minus k0 minus 1, then of course the starting of a bad sequence, then I is not available. Now what can happen? Could be that we are here at k0. And then we have here 2 points, 2 indices, which are bigger than k0. But then we use that this sequence is bad. Then use badness SKI. So what else? What can happen? Well, it can happen. One index is here, and the other index is here. So, now consider the situation. We have here some TI, and here's some element SKL. I is this is crazy on this one. So one term sits here, the other term sits here. Is this possible? Well then, it's in SKL. But SKL is this form. Now TI can embed it into SKL. And TI can be embedded into the longer sequence by just moving this term here in the second component. But this is the same as TKL. And TI would be embeddable in the later TKL. Contradiction with TI effect. That's fine. But we are not yet done.
Yeah. Do you say that SKL is the same as QKL SKL?
That's for construction.
And maybe I got it wrong. What do you mean then with TL is?
TL is a finite sequence starting with an element in Q and then some other finite sequence.
Yes, yes. And then like only in the first element is Q, and then we have SL.
Is anything Q star. So every finite sequence can be written as first element and another finite sequence. So it's a what is called head and tail in computer science. The head is QL and the tail is a subsequence.
Okay.
And you see, the proof is beautiful, but you still don't see what's going to happen, right? Just what we learned is no that subsequence in this shorter sequence escape. Okay. How we claim that the sequence SK contains an infinite weakly increasing subsequence. Why is this the case? It's completely mysterious. So, claims it's okay. Contains an infinite weakly increasing subsequence. Well, why should this be the case? Well, the trick now is define a function the partition P. P grows from pairs of natural numbers into set with two elements. So what we do is we will apply Ramsey's theorem. So Pij as what? Become 0 if Si embeds into Sj and 1 otherwise. So we have a partition of pairs of natural numbers into finite set. Ramsey says there's an infinite homogeneous subset. Let A be infinite and homogeneous for B. Now the question is, what is the color? Just assume if P in respect to H is color 1, then we can enumerate the elements. So we enumerate H, one increasing way. The ith element is an enumeration function index I. And then we get a sequence elements indexed by the elements in H. And if the color is 1, then this will be a bad infinite subsequence of this. But this one does not exist. Therefore, the color is not 1, its color is 0. So, color is 0. And then we enumerate the elements of some new set, and then this will be a weakly increasing subsequence. And S enumeration function of H applied to I is weakly increasing. Increasing with respect to this order. I just recognized I made a small mistake in the construction. I was claiming that SK has no infinite base subsequence. And the truth was not fully worked out. So there exists this sequence, that's fine. Now we have found this one. And I claimed that this sequence is bad. That it was correct. But now even this bad gives a contradiction. Because when you look at this sequence, at position K0, the length of SK0 is shorter than the length of TK0. So the existence of this sequence contradicts the minimity of the minimal bad sequence TK. So therefore this is a contradiction. Therefore, this sequence has no infinite bad subsequence. And this is what we use here. And if the color is 1, and this would be an infinite bad subsequence, but this doesn't exist. Therefore, this is the color is 0, and you get a weakly increasing subsequence. So I missed a small argument, but anyway, so this is an important issue. Actually, a crucial issue. Namely, looking at this situation leads in the proof to an important contradiction where the minimality of the original sequence was used. So here's the point. Yeah, I plugged in a shorter term. Anyway, I have now a quickly increasing sequence. Now, consider. So I write for this AI, this enumeration function of HI. Consider the function, the sequence U AI. In the whole proof, until now, we have not used that the original order was a Weltquasi order. And the claim is if Q is the Weltquasi order, then Q star is the Weltquasi order. And up to now, we haven't even used the Q as a Weltquasi order, but it comes now. Namely, we take these indices, and now we form an infinite sequence of elements in Q. This Weltquasi order. So this means there exists I less than J, such that Q AI with respect to Q embeddable into Q AJ. Now finally comes the trick. Then what does this mean? We have here T KI. It is starting with the element QKI. Then comes SA. Here we have TKJ, which is KJ extended with SK. Now what? This sequence here is embeddable into this sequence here, because this sequence is weakly increasing. Moreover, this element here less than equal to this element here. What does this mean? This means by mapping this element into this element and using everything from this subsequence into this subsequence, we finally obtain this one. This is great because that's a final contradiction, because finally we see that the minimal bad sequence is not bad at all. So they does not exist. But you see, this is a sort of nice argument. You have nothing in hand, no structure, and then you start some argument, and suddenly the result comes out. And you can, well, I guess you can agree that it's difficult to find, but it's just, and it's also a beautiful proof in the sense, when you have seen it, it's just pure magic, right? Now, what we now do is we prove the corresponding statement for finite trees. What is the claim? We have finite trees for them T. The invariant relation is very tight. Assume. Is there a question? Yeah.
When you choose LH0 minimal, do you pick a random T0 or do you?
Yes, it's a random T0. The only thing is that among all first components, you choose one, and the length of T0 is minimal. But there will be many of them, very somehow possibly uncountably many such sequences. But all these sequences have a length of a first element. And then you have a non-empty set of natural numbers, and every non-empty set of numbers has a minimum. And then you just choose among all infinite choices just one. So basically some sort of, you can say, axiom of choice or whatever. So that's non-constructive. Depends a bit on your data structure. Or effectively your set Q is given. But if you have no information, oh well. Yeah, we have no information to say. Just among all sequences, we choose one where the first element has minimal possible length. And how we find it can be arbitrarily non-constructive, but it doesn't matter. It's just.
Would it also work if you just cut off elements from the left?
Yes, I could also do. Let's say I could also write K as SK in all be fine. So the same proof would work also this situation. But then I would have to move this term to the right, this term to the right. Then you see it's also going to work. But, it doesn't matter. So now continues our beautiful construction. So this is a backfire problem. So what do we assume? That there is infinite bad sequence of finite trees. Okay. Now we construct a minimal bad sequence. So what we do is now, among all bad sequences of finite trees, we choose one where the first entry has a finite tree of minimal possible number of nodes. We just, instead of the length function, we now use the canality of node function, right? Among all sequences which are bad, there exists one sequence where the starting term has the number of nodes in the starting term is minimal. Then we consider all sequences starting with this term, and then we choose the second component minimal. So and there is a minimal bad sequence of finite trees. Now minimal with respect to the number of nodes. Okay. Now we do something similar as here, namely we write finite tree in simpler terms. So for any k, let tk n to n be a listing of the immediate subtrees Okay. So TK as which form? It has a root. And then here are the immediate subtrees just sprouting off from the immediate successors of the root. They come with some listing. And I just choose them. And NK is the number of immediate subtrees. Now I make up a set. S, the set of all EKM. So it's similar as before. And now we do something with the shorter trees. Claim is S is respected the orient. It's a very class. Okay. Otherwise, there exists an infinite bad sequence in S. Otherwise, there exists infinite bad sequence. PKI MI. Okay. Someone the set find an infinite bad sequence. This is coming with these indices. Now it's important that I have here, if I fix some ki, then how many trees are there having index smaller than ki? These are finitely many. Now there are finitely many trees which have an index smaller than ki. So what I want to claim is, in this infinite bad sequence, we can basically find another infinite sequence such that the indices here, the ki, are strictly increasing. Why is this the case? Because if you fix some ki, if the whole rest of the sequence would stay here, then I would find an infinite bad sequence in a finite set. This does not exist by pigeonhole principle. So it's a complication, but not a difficult one. So by pigeonhole, we can assume the pigeonhole principle. We can assume ki smaller than kj for all listening. Now why is this a contradiction? The argue basically as before. Consider the sequence of finite trees. Here, the first t k0 minus 1 many. Then we have tk0, n0, tk1, n1. Now what? We claim that this is a bad sequence. Why is this the case? Well, choose an instant pilot in J. Could be that they are over here. J is listening to K0-1. But this is a contradiction with the badness of the original sequence TK. Can I find pairs over here? The answer is no. Because this is bad sequence. So the only thing what can happen is I is living here, J is living here. Now I is smaller than K0 minus 1. J is bigger than K0. Then well, then what? Pi. Well, J is one of those. J is, let's say, some KL. Pi. Assume that this is embeddable to TKL. It's possible. But TKJ, MJ, the elements here have this form. Now this is an immediate subtree of TKJ. Right? TKJ is this as an immediate subtree. So TI is embeddable into immediate subtree of TKJ. And you can move the tree into an immediate subtree of another, and you can embed the first one into the whole tree, just using the same embedding. And so you get TI embeddable into TKJ. KL. Anyway, doesn't matter. The argument is the same. Contradiction. Contradiction? No. You've just shown this is bad. Fine. But now, since this sequence is bad, we get a contradiction because here at position K0, you have plugged in the shorter element with the number of nodes in TK0 N0 is smaller than the number of nodes in TK0. So this contradicts the minimal choice of TK0 in the beginning. So finally, we get a contradiction with TK minimal base. That's good. Great. And now. Now what we have seen is that's quasi order. Then we have a star. So that quasi order. A star is a set of finite sequences. Okay. Now let TK Now you have to be careful. It's not a finite tree, but it's a list of finite trees. And the list of immediate subtrees of TK. So this is an element in S star. This is the quasi order. So find I less than J such that I is less than equal to star J. So what? Well, consider here we have TK. This TK1, TK NK. So here's TI, let's say. And TJ is over here. It's TJ1. TJ J. Okay. So what do we know? We know that this list here, the sequence of immediate subtrees here, embeds in this list of immediate subtrees over here. So this tree somehow embedded here. X1 comes later. So we can move all the immediate subtrees homomorphically into immediate subtrees over here. And finally, if this is possible, then we move the root to the root. Ti is embedded into Tj. And contradiction, because finally you have seen the sequence Ti is not bad at all. And as I promised, this is a nice proof, right? Just mathematics with bare hands. You have a simple structure, and you do some argument. And why is it so complicated? Because the transition from a bad sequence to a minimal bad sequence requires, in the definition of these natural numbers, or the construction, the infinite bad sequence requires comprehension. And there's a quantifier involved, namely about all possible bad sequences. So it's a comprehension about infinite sequences is a sort of impredicative comprehension. This makes it somewhat complicated. And therefore, it's also very difficult to find this proof. And the point is, you cannot find a cheaper proof for Goodstein's theorem because there are these results in logic where you can prove what. And Goodstein's theorem cannot be proved in simple extensions, second-order extensions of Peano arithmetic or something like this. Okay, now it's 11:15. We can make a break. In the meantime, I could check. The number of participants is too small. Okay, now we have seen this infinite one. And after the break, we will
Not from the museum. Yeah.
Okay, now we discuss Friedman's version of Croswell's theorem. So let F be a function. And in the original statement of Friedman, this was an identity function. And Friedman's version of FKT, Friedman's version of Croswell's theorem is with respect to function F. It's the following version. Just about finite objects for every k with n. Such that for all finite sequences of finite trees, if there's not a chaotic sequence, meaning that this is somehow controlled with respect to the number of nodes. So if you have a linear growth rate condition, or growth rate condition controlled by f, there's a number of nodes in tree Ti is bounded by n plus f of I. Then, and this is I and j, that I is this and j, and the I is in negative. Now the question is, of course, what is complexity here? To assume for simplicity f is identity function, and k is, let's say, 100. We fix k, then basically you have here existential statement. So it's known that true existential statements can be proved in arithmetic. So there exists a proof in pure arithmetic of that statement, but you will not be able to write it down on a sheet of paper because the proof is so long, the number of steps needed, number of simultaneous steps is much bigger than the number of atoms in the universe. We have a true statement that it's known that you can prove it. You cannot write it on a normal sheet of paper. So it's interesting. Actually, these numbers m are much, much, much bigger than the numbers coming from Paris Harrington or also Heidelberg. So these are really big numbers. Of course, we don't see it yet, right? But if you want to win a party game with who can name the biggest natural number, just 200 over here, and say this m is sufficient. You will beat 99% of all other people. You only lose against people who know about this stuff. And of course, you can start with hundreds and say, take k to 101. They win. Anyway, the theorem is theorem of Friedman. Well, the simple version is FKT F is true. The interesting theorem is FKT for the identity function is not provable from strong systems of analysis, but we will not cover this one, at least not yet. Well, we will cover the growth rate a bit, and then we will see it comes strong. But not just why it's true. Cool. And as usual, when we have statements like these, there's a universal proof principle, which we used several times, and it was Koenig's lemma. So this is what we are doing here. So what we need is we need a a new sort of tree. So these are the finite trees from combinatorics, but now we use finitely branching infinite trees. These are sets of sequences. Right? Let now a new sort of tree be given by D. Consists of what? The nodes are given by sequences of finite trees. And these are finite bed sequences. So there's no thing, so it's I is available in J. And the sequence is your control. Great. So that's a set of finite bed sequences. I'll assume F is false. If there's some K, such that for all M, there exists strange trees. There are trees P0 to M such that all I is equal to M. We have number of nodes of the I point by K plus F of I. And sequence is bad. No I is in J is equal to M such that the I is embedded into Tj. What does this mean? This means that this set here, this set B, is infinite. All M above a sequence of length M. And B is infinite. Now, if a sequence is in B, then every subsequence, every strict initial segment is also in B. So B forms a tree-like structure. Now the question is, if you have such a sequence, how many extensions do you have? How many possibles are there for Tm? Well, for Tm, there's a condition on the number of elements. And of course, there are finitely many extensions of a sequence. Because, with a bound on the number of elements in Tm, to see if you have a sequence of this, you want to plug in another Tm. The number of possibilities to plug in another Tm is bound by this one. There are finitely many possible extensions. So what you have is B is infinite and finitely branching. So you can apply Königs lemma. And this implies there exists an infinite branch in the tree. So there exists a sequence, empty sequence, and then you have a sequence T0, T0 T1, T0 T1 T2. Okay, so there's a way to go into the tree. You get the transfinite list of extensions, but then in the limit you take the sequence Ti. This is an infinite bad sequence. Contradiction is theorem by Goodstein. Okay, that's it. So by magic, we have now Friedmann's theorem. Now, what's going to happen next is I need some elements about counting trees. But since not too much time is left, I will just write the counting results on the board. And the stuff is to some extent in the notes which I put on Ufora. So I do the following, namely, the point is what's the number of finite trees T such that T is n nodes. A good question. But this is basically following. Asymptotically equal to alpha to the n, n 3/2 times the point. It comes from the theory of tree enumeration. So basically, you have some sort of exponential law, and alpha is some sort of strange constant, which might even be transcendental. How to describe alpha follows. So let rho be the radius of convergence of the following power series. Is sum over n to the n from 0 to infinity, where P of z is z times the exponential function from 2 to the n infinity. How about this? So we assume that we have power series, and the power series satisfies the law. Then one can show rho is bigger than 0 and alpha 1 over rho. Now that's a sort of funny thing, but the point is, if you have a counting problem in discrete mathematics, quite often you have to use generating functions. And this power series here, the generating function for counting finite trees. Now, since we are counting finite trees, we have a complex situation. Now, what is the explanation here? Basically, a finite tree has a form, it's a root, and there comes somehow a multiset of immediate subtrees. Now, this factor z comes from counting the root, and a construction like this is used for if you have a counting for class C and you form finite multisets over C. The counting follows a certain, those generating functions for the new system can be used, can be calculated in terms of the generating function from the original structure. That you're counting these immediate subtrees has to do with a specific form. Some more details can be found in the book by Donald Knuth on the art of computer science or whatever. There's a famous book by Donald Knuth. There's 5 books about the art of computer science. And this is one of the books where he lays this down. There's also a famous book by Flatley and Setchwick. About the analytic combinatorics. Now, this book has an advantage. It's free download from the website of Philippe Flatley. And it's all about how to find these generating functions and whatsoever. Okay, that's it. Now let's see the mysterious constant, namely 1 divided by binary log of 1 over rho. It will be bigger than 0. It's basically about 3.6. And now the next theorem is A. If R is less than equal to C, then what's the delta proof? If R is a function R times binary log. If R is less than equal to C, then PA does prove F delta T R. And B, if R is bigger than C, then A does not exist. And that's basically what we want to show in the rest of the lecture. But you see here, there's one constant where there's this threshold between slow growth and big growth, and it comes from the function times binary log. Yeah.
When you say dz is z times the exponential.
Yes. It's not a definition, it's an implicit functional equation. So there exists a power series making a solution for this functional equation.
And that will always be true.
I'm just claiming that there exists some power series making a solution for this one.
Yes.
It's not always the case, but this equation is true for if I write down this T of Z with this property. But of course, I can just claim, forgetting the power of this one, taking a power series, which is the solution of that one, a rho is a radius of convergence, and then alpha is 1 over rho, and that alpha fulfills this property. Now the reason for this is if you have a normal power series and you have the radius of convergence gives some bound on the growth rate, the coefficients, let's say a sort of exponential bound, so to say, and that's also used in this context. But I just use the counting, and now what we will see today, it's easy to show the first part, relatively easy, but it's very difficult to show the second part. So we prove A. And now Tn counts the number of trees with n many elements. Now the problem is I need all the bound for T less than equal to n, which is the sum of Ti I is equal to n. And I need also asymptotic information about this one. Now I will now not go into too much into the details. Then the asymptotics for this function is basically the same. It's another constant times alpha to the n and 3 over t. And this has to do with certain properties of power series. This follows by a theorem by Polya. And this is in my JSL paper, which I put on Fora. And this is sort of, if you know the information about your power series, and you multiply the power series by 1 divided by 1 minus z, this will not change the radius of convergence, say. Therefore, this type of law will remain. But you can also some sense believe that this is true because you have an exponential, and basically when you sum an exponential, then basically the last term is most important. This is not an argument. The argument is formal theorem by Polya. But I will keep it as a guard. It's somehow important that I have here 3/2 and not 1/2. We'll see it in a minute. So what? We prove this statement. This one. It just disappears. Not so good, but anyway. Let K be given. Now I want to find an upper bound for the number m such that all finite bad sequences of length m that all sequences of length at least m will not be bad ones. Okay, let K be given, and m. For simplicity, you can assume that K is big enough. K is bigger than binary log of 1.1 times constant divided by 8 to the d times c times alpha divided by 8. That doesn't matter that much. What is d? I didn't explain it, please. Good question. So assume p less than equal to n is bounded by constant alpha to the n 3/2 times 1 plus 1 for n at least as big as d. So if this is asymptotic equality, then if I make this a bit bigger, then of course for large enough n, this number is bounded by this number, which is made a bit bigger by 1.1. Now I say m. M is 2 to the 8 k plus 1. That's all. So very simple upper bound. Just an exponential, double exponential, and this will be sufficient. So assume what? I from k to the n is a finite sequence finite twist such that I is bounded by k plus r times binary log of I. And assume there are no indices such as Ti embeds in the. Okay, what do we have? Then, since you have a bad sequence, all the trees have to be different. Because if in a sequence 2 elements are the same, the first embeds into the second by the identity. So the I's are all different, and moreover, we have the number of nodes in Ti is bounded by k plus r is less than equal to c, so I can make it bigger. Times the last element is m. And when? What's no finished. And then what? Now I get here a sequence of lengths m plus 1. So m plus 1 is less equal to the number of fields t, such that t is number of nodes in t is bounded by k plus c times binary log of n. Now here we know this is bounded by here we have the tree counting, so constant times alpha is what? The number, call it m prime. Times 1 plus 1. And now I'm claiming this is smaller than m. Then m plus 1 is strictly smaller than m, and that's not possible. Now, the question is, of course, why is this the case? Well, let me show this one. So I multiply this to the right. So let's hope that everything is okay. So I have m plus 1 times constant. I have here alpha a plus c times binary log 2 to the 8k plus d. So here I get 8 to the k plus 1. And here I have 2 to the 8 k plus d. And I multiply with k plus c times binary log of then what disappears 8 to the k plus 2. 3 over 2. Okay. What do we learn here? First of all, we have this. Now alpha. What was alpha? Yeah, alpha is this one. So alpha is 1 over rho. And C was 1 divided by log 2 of 1 over rho. what we do here is we write here alpha is k. And alpha is 2 to the log 2 alpha. And c is this one. So you see this cancels out. So what's going to happen here is 2 to the 8 can this cancels out. So what do we have to show? We have to show that 1.1 times constant property k is bounded by this one. Over 2. But that's correct because alpha is basically bounded by 3. And alpha to the k is bounded by 8 to the k is another 3 over 2. So you see when you fill out a bit with the details, it turns out to be correct, right? Yeah, that's it. So it's a bit of magic, but what you see here is what is the point? The point in the proof is the moment where I cancel out log 2 of alpha with the number c, which makes this term into this term. And of course, I'm going higher with the r, then it does no longer work, this argument. When this canceling is no longer possible, then the argument breaks down. Well, just when you write down the arguments, you will recognize this nice proof depends on the property that r is small enough. Then you can make an easy estimate, and then the result comes out. But when r is bigger than c, the argument breaks down, and then complexity jumps. Okay. Now, of course, you can imagine things will become interesting. Because now we prove the other part, and now this works by a sequence of reductions. And the most difficult part is the following, namely, we use first another result by Matuszek and Löbel. And what did Matuszek and Löbel show? So let us report the F R following the certain K is 10. Object for 0 to n. If for L is equal to n, we have Ti is bounded by K plus R times binary log. Then there is this I in J of m, so K plus I is better than that. And Matuszek-Löbel showed PA does not prove FKT as number 4. Now what we will do is we will show FKT as 4 and thus FKT as R for all are bigger than all critical constant. We make a reduction. And then, since this is unprovable, what we will show is what? I will show this one. what do we show? Let's see. No, we show this direction. And this one we show this one. Now, is this provable? And this would be provable, but this is unprovable. Therefore, this reduction is fine. Then we go further to show from FKT F4, we can go to higher function, going further and further. And at some moment, we will show one of the versions will imply the Hydra statement, and therefore all the statements are not provable in the house. Okay. Now we need another result. So this is what we are going to prove. Now, the proof of B in stages. And now Tm of n, the number of trees T such that there's n nodes and every node in T has at most m immediate subtrees. So this is a subclass of all finite trees. And then one can ask, what is the asymptotics of Tmn? It will be constant depending on m times a modified tree constant depending on m, gaining exponential log. For certain alpha m smaller than alpha. Now, for this, you have to write down the generating functions and use this. And on Ufora, you find a paper by Go and Schmutz. And they do the following. They show that the limit of the alpha m's, m going to infinity, is equal to alpha. Now, this is one statement, but they prove even much more. They even give a rate of convergence. And this convergence is exponentially fast. And what we don't need, but this is a high-level paper on tree counting. We just need this property. And this is somehow, yeah, it would take me 1 hour to prove this, too much. So I just use this result. Okay. Now we have what? We want to prove B, R is bigger than C. This means find number m such that R is bigger than 1 divided by the binary log of alpha m. Now choose a rational number. Between R and 1 divided by the binary log of alpha m. Okay, now do some asymptotics, namely find number E such that for n that is equals E, we have asymptotics applies. Emn is at least as big as alpha mn times constant for m times n minus 3/2 times, and now makes the number bit smaller than 1, let's say 0.1. Moreover, find number D big enough such that for I equal to D, we have times binary log. I is against E, that's fine. Log is divergent. And n plus 2 times Q binary log of I. That's 4 times log of I. Followed by R times log of I. So it's Q smaller than R. This term is smaller than this one, and log grows faster than log. So this term is eventually dominating this term, and you can easily find out number D where this is going to end. Now, how the magic will start. So we assume proofs of F, A, E, F. Now it means for every K, there's an M. So we start with some K. So what I want to show is, I want to show multi-check label for number 4. I want to show multi-check label for number 4. I take a K for this assertion. And this K is transformed. So let K be given. Then make K a bit bigger, K bar. Let's say K plus B plus M plus B. So basically K. This K bar is now an input for FKT FR. For K bar, find with FKT FR an M such that all sequences of binary trees, of all sequences of trees, E0 to the M, such that for I equal to the M, we have number notion I is bounded by the syntax plus R times binary log. We have this I less than there, such that I is equal to. Okay, now we claim this M is good for KT. Okay. So why is it the case? So given K, I have now found an M. Now assume that I have given a sequence. Let E0 to Tm be given. That number of nodes in Ti is bounded by K plus 4 times binary log. Aha. Now the problem is to apply FKT FR. I need here an R and not a 4. So these trees are too complex. Now we go to new trees. find trees VI as follows. And it's somewhat complicated. So VI consists of one situation, immediate subtrees VI and VI. And the root. And so VI as a form, CI. Okay. Now to say what is CI, what is DI? DI find spot. Now we have to remember when we did the proof of Harris-Harrington, we wrote down a sequence of ordinals, and in the beginning, we first had some sort of trivial ordinals. We did some padding, just subtracting ones or whatever, and then at some moment when the asymptotic was applying for counting functions, then we did some real construction. The same is going to happen here. So there's a bound, and there's a number D. D is from the vertex. So for I less than D, DI is a linear tree with D minus I nodes. The DI is a simple form, it's just tree like this. And then you have I mean this. So what is going to happen when I becomes bigger, the tree becomes shorter. So this is clearly a bad sequence. You can imagine this is just for some technical reason. Now when I is big enough, then our tree counting applies. So if this is B, then I is the 2 to the binary length of I minus I element following set M R times final log of I. It's a bit of one trees such that T has R times final log of I number of elements, and branching is bounded by. Now, what is this? So you have a set of trees. And on this set of trees, we have an ordering. We have a set of trees. We have the homomorphic embeddability relation. Now I can show the homomorphic embeddability relation is a partial order on finite trees. Now every partial order can be extended to a linear order. So we can take some linear extension of this ordering that is fixed, and then with respect to the linear ordering, we choose this corresponding element. Okay, and that is di. Okay, now we know what di is. What is the point here? Point here. Question. I made a mistake. Let us take U. Yeah, U is smaller than one. I take Q. The point is that the complexities of these streets here have small complexity. Complexity is measured by this function. You see it here. This function is measuring this function. Okay. So what is the idea here? We start with a sequence Ti. Now we try to compress it into one of lower complexity. Oh, this is possible, but we can lose the badness property. When we compress too much, some trees might become the same. That's bad. So we have to prevent that we move the tree sequence Ti into a sequence which is good for some trivial reasons. Okay, so we are counting this one. Now the question is, what is Ci? We have Ci. Is a tree with unit subtrees. Now for I smaller than D, EI will be a trivial tree. That's the constant tree. And for bigger than D, okay. I now I take ET. And that's important. I take my original sequence T, but now with index log of I. So what is the shape of Ci? It's basically, I is big enough, T log of I over here. We have seen such construction before when I did Barrow-Harrington. I was starting with a descending sequence of ordinals, and then I moved into the new descending sequence of ordinals, where from alpha I went to alpha index logarithm of I. Well, that is going on over here. So I take 3t, and the index is the logarithm of I. Now the question is, what is f of I? F of I is always the constant tree. It's of the form just one root n plus one many direct successors, singleton nodes. So Pi has this form. Now, what is the general shape? Now we need a picture. So what is BI? Assume that I is big. And we have basically the following situation. Here is we count here 2 to the binary log of I as element. That's 3 over here. Now on the left, I have the situation. Here is the tree with out degree n plus 1. And basically here it's E of I. That's basically the structure. Now the question is why I'm doing all this. First of all, it's important when I have this class M, I made here a condition on the branching. Here the branching is M plus 1. Now why do I this type of construction? Because in general trees, you have no control that if you do embeddings, that the left tree goes into the left tree and the right tree goes into the right tree. But if you have a tree here with out degree M plus 1, such a tree is never ever be available into such a tree, because here this tree has out degree bounded by M, and here is one with out degree M plus 1. So this is just a coding trick to say this is the left tree and this is the right tree. Just by some sort of artificial construction, I make this tree always to the left and this tree basically always to the right.
And then you write enum and then
Enum is an enumeration function, and here it's the basically binary length of I minus I.
that's almost 0.
Not really. So 2 to the length of I. Yeah, maybe I'm plugging here. That's one. Maybe I use here the function. That's one, but this is somewhat minor issue. But of course, I want to have always that I is smaller than this number. So I want really to count, to be able to count down here, to have here enough space left. But now let me explain the rest of the argument. First of all, what can we say about BI? Is it all well defined? The number of nodes in BI is bounded by what? Number of nodes here, number of nodes here, number of nodes here. It's therefore bounded by the number of nodes here is bounded by A plus now Ti is bounded, the number of nodes in Ti is bounded by 4 times log of I. T index log of I is bounded by 4 times log of I. Plus, what else? Here comes some nodes. 1, 2, plus M plus 1, plus, let's say, whatever, 2 plus, and then comes here the complexity, which is what? U times binary log of I. And what I have to notice is that this is bounded by a tilde plus r times binary log. So I have to arrange k tilde that this is going to be true. And I large enough that r times binary log of I is measuring this term and this term. And of course, if I is smaller than d, what then makes this k tilde big enough so that the same estimate also holds for the beginning. This is for I bigger than d, but also for I is. Now, next trick is now I have a sequence of BIs for my k tilde. I know by FKTFR I find I has a day such that BI is embedded into BJ. Okay. And there are three cases. Could be that I and J are smaller than D. That's impossible because the DIs in the beginning were just cutting off nodes. So the number of nodes in BI is bigger than the number of nodes in BJ. So BI is not embedded into BJ. So this is not possible. Now there's a case that I is smaller than D and J is bigger than D. And that's very similar to the case that I and J are bigger than D. So let's assume the critical case, but you can fill in the details easily. That assume that D is equal to I less than D. What can well, we assume here, as usual, that we have here some rounding. So we take here some integer part. And so we assume that log 2 of I. I have to be careful. I put in here I plus 1. Let us assume that I have here also I plus 1. This doesn't matter that much. In the whole construction, I just whenever I use my log function, I specify this function. This is also the binary length function. So I assume that this one same as this one. And so my claim is that this is impossible. Now, why is this impossible? So we have here BI having this thing. Compatible into DJ. having this simple form. So what? For this one, dk, and this one here is dk. This one is I. So we know this one is embeddable into this. What could happen? The question is, the root has to go to some place. Is it possible that this root goes into this tree here? The answer is no, because if the root here would move into this tree, I had to be forced to deal with the m+1 branch. This is impossible. So I, let's simply dj, is impossible. Since dj consists of maximum m branching trees, because branching in dj is bounded by m. Okay, now we assume that this one is the same as this one. Is basically, I call this binary length of I, this binary length of K. Here would be T binary length of I, and here's T binary length of K. And this node be moved into Cj. The answer is no, because this tree here is identical to this tree here. If I would move this term here into one of those, then the whole tree here, the number of nodes here is just more than the number of nodes here. It's all the nodes here. So what is going to happen is the root here, you go into the root here, right? Now, the question is, where does this point go? Can this point go into this tree? The answer is no. It's the argument with the out branch. So this node has to go into this part, and this, and then if this node goes into that part, the root of di has to go into dj. So the root of di is mapped to root of dj. Now root of ci cannot be mapped into dj. Hence, so root of di is mapped to dj. Because if this would be moved here, and this one would be moved into this one, then the infimum of those 2 points would be here, but the infimum of this point is this one, would be this one. So necessarily, this one has to be moved into this one. Okay, and now we see what's going to happen here. We have di and dj. And now what we see here is that di measures the dj. Both of them, let's say x of 1 and length of 1. MR times binary length of I is the same as MR times the binary length of J. And this means that DI is 2 to the binary length of I element in MR times under I. And J is J. So this means that the I is less than equal to the J. This means in the linear extension here, the I is equal to the J. But now J is bigger than I. So 2 to the length of J minus J is what? Is smaller than 2 to the length of I minus I. So I minus I, J was bigger. Length of I length of J. So in the enumeration, is what's going to happen? Dj is smaller than this element comes before this element. So dj is smaller than di. So di is in the enumeration coming before di, that's impossible. Therefore, this is not possible. Therefore, this means this case is impossible. So what is going to happen? It's going to happen that finally, we have the case that prime length of I is bigger than what? J is bigger. Okay. Now this tree is embeddable into this tree. And we do again the same argument as before. This tree cannot be embeddable into this part by canonical arguments. This tree cannot be embeddable into this tree because it's a branch. So if this is going to happen, then the root has to go into the root. Now this tree has to go into the immediate subtree over there and vice versa. You can see the branching m plus 1. This tree has to be embedded into this tree, and this tree has to be embedded into this tree. Okay, so let us consider the situation. This is going to happen. Now what? Then this tree, this node, can the root here be moved into this immediate subtree? This is impossible because here the height is at least 2, and here the height is 1. So we cannot move. So the root here cannot be moved into one of the nodes by here. Could be, and this one moves into this tree. But if this one, this node here, moves to this tree, that follows that E finally next of I available in E. Right? But in this case, we have found the pair for Matuszek-Löbel. Namely, we have two indices, one smaller than the other. So that in the Löbel sequence, this tree is available to this one. So that's fine. Okay, therefore, let's assume the root moves over here. Now, what can happen? It can happen that the root here goes into this tree. But if the root here goes into this tree, again, T binary length of I goes into tree binary length of J, and we are done. Or this node goes into this tree here, but then this tree has to go into this. So if Ti embeds into this strange tree, then this tree is to go to T. But then you see by transitivity, this moves into this moves into this. Again, I moves into J. So with some back and forth modifications, that's the argument. So now, how to think about this? Well, the idea is compression. Namely, if you have a tree sequence which is too complex, go to a new sequence which is more compressed, and try to use what you have for the compressed sequence. And that's it. Now there's one trick, namely we are not yet done. Namely, you have something is not yet clear. Namely, here I used that I have here this element in the set. The question is how many elements are in the set? And I need that this set has enough elements so that I can apply it to this argument. But this is possible. That's the last step in the proof. That's a counting argument. Let's see whether I have written it up. No, I forgot it. Anyway, it doesn't matter. So use this one. So what do we need? Plane. We need that M R times binary length. Let's say. The number of elements in it is at least as big as 2 to the binary length. Now for this, we use our counting. So the cardinality in MR of P. Number of elements in MR of I is here I have this form. It's at least as big as alpha M. Then N is the R times binary length times constant times N is R times binary length times 0.9. And now we have to show this is at least as big as the binary length. Now, what else do we have? Alpha M R times the binary length of I, the same as 2 to the log of alpha M times R times binary length of I. And now you see the magic. R is bigger, so this is bigger than to the R is bigger than this number. So we get here 1 plus epsilon times the binary length of I times some rest bigger than the length of I. And that's the space we need, this small r, bigger than this number, making this factor bigger than 1, and then we are done. And but here you see also why I need the convergence of this log alpha m to the critical constant log of alpha, so to say, because it's needed in this argument. And this is basically finishing up the argument. But you see how nice it works. And now, what is the next step? I will finish now, right? Don't worry. The next step is from FK the 4 times binary log. I will prove FKT of let's say I to the 3. And then I go to FKT of let's say the square. And then I will show that this implies the aeroplane. But don't worry, the step today was a crucial and difficult step because I was in the neighborhood of the critical constant. Now I'm away of the critical constant, and then the divergence to infinity is going really fast. So all these silly details will just disappear. So next time I will just show this one by one-liners, basically. But what you have to do is basically you have to reiterate this construction all the time, but just replacing the bound on the TI is now not 4 times the binary log, but just let's say the exponential. But then if you go to log, you go from the exponential to a polynomial, and then you can go there. So basically the point is, if you apply this procedure, every complexity F of I goes to complexity log of F of I. And if you apply this transformation several times, you reduce the double exponential function to an exponential function, to a polynomial, to a linear function, and then to a logarithmic function, and then you go to the multi-cyclical function. That's basically it. Okay, so much for today, and Don't worry, that was basically the complicated stuff for today. But it was a bit messy, maybe. But you can imagine that I was quite happy with this. And in the literature, you will find now this constant C. Some documents is constant by Weiermann. So that's my constant, so to say, and you see how it goes. Okay, thanks for being in. And yeah, I hope that next time the others are showing up. Yeah.